All right, here we are. So now, if you take a look at what we have here, um, in this particular case, we were getting back to the maximum silver rate problem, in which they were talking about differences between relative maximums and relative minimums, and trying to figure out how to optimize a given problem. So now, if you remember correctly, how this whole thing went, they were talking about an actual case in which we're trying to maximize our solution of buying low and selling high, right? So you have day one and you have about 17 different days, and you are going to try to get the lowest valley, sell at the buy at that lowest valley part, and then sell at the highest of peaks. Now, one thing that was unclear, and this still applies because going forward you can't see the future. Going from day zero to day one, that was the highest climb there was, and there was never ever another maximum that large again. That was part of the point that they brought up. However, if you take a look at seven, that was the biggest low. So the difference between the lows and the highs varied. In this case, the lowest of the lows was seven, and then the next high that would come later would have been at 11. All right. That's about as maximum as the investment could get. Now, the thing that they're trying to show us is, some sort of an analog in which we are basically investing in futures, right? Where you have like some sort of a stock option almost to buy, but you don't have to buy unless you wish to because you don't know what the actual price of the security will be. The only thing you know is that, there's a certain security that sells for a certain value. The price could fluctuate. Here's what it is today. Maybe you'll want to hold or buy and hold and sell at a later point in time. Now, they told us in our partial solution the following. They said, comparing two different days may be difficult. Instead of comparing the price, which is what you have up here on different days, what we want to do is try to compare the change in price over given intervals. Okay. So just backtracking a bit, it said the following. You might think that you can always maximize profit by either buying at the lowest price or selling at the highest price. But in this example, figure 4.1, we will maximize profit by buying at the lowest price after day 7, despite the fact that the highest price was on day 1 after day 0. If this strategy always worked, then it would be easy to determine how to maximize profit. You find the highest and lowest prices, and then work left from the highest price to find the lowest price that was prior, right? So this guy here looking at the lowest. But in this case, you have this guy here, and you're looking for the lowest price going backwards. And you're finding that 7 was the lowest of all of the lows. So now, in this particular case, if that did work, then we could kind of take some sort of, or we could kind of consider that to be some sort of an answer for us, right? Now, figure 4.2 shows us a counterexample for why that won't work. If we were to try to take the highest and the lowest, right? The highest here would only take us back 1 day. The next highest would also take us back a single day. But in this case, we can see that the difference between 2 and 3 is greater than the difference between 10 and 11. I'm sorry, between 0 and 1, right? So going from here to here, that's not such a big jump, but here to here is a bit more dramatic. Okay, so now the maximum profit doesn't always start at the lowest price or end at the highest price. Instead, we may want to use a different type of method. So the horizontal axis indicates the day, the vertical axis shows the price, and then here we got the maximum price of $3 per share. And that would be earned by buying after day 2 and selling after day 3. The price of $7 after day 2 is not the lowest price overall, and the price of $10 after day 3 is not the highest price overall. Okay, that's what that tells us. So now, if we look at the changes though, you notice that from 0 to 1, that a change of +1. From 1 to 2, we had the change of -4. From 2 to 3, we had to change a +3, and then finally a -4 again. So now, here's the brute force solution. I mentioned that yesterday. You know, a person who doesn't know any better may want to try to take all combinations of dates or pairs and then see what the differences of them were. But now we were told that this would take omega of n squared time. And the reason why is because we're taking subsets of the power set to see what is ending up as a maximum difference between price range. So now here they're talking about something called transformation, in which we do something different in the case of trying to trying to figure out the maximum subarray. Okay, so now in order to design an algorithm that is better in its running time, we'll look at the input in a slightly different way. We want to find a sequence of days over which the net change from the first day to the last is maximum. Instead of looking at the daily prices, let us instead consider the daily change in price, where the change on day I is difference between the prices after day I -1 and after day I. The table in figure 4.1 shows that these daily changes in the bottom row are what were recorded. So the difference between 100 and 113 is a difference of 13. But now you take that and we talk about the difference between that and 110, and it's -3. So that's not really what we want. So that's what we're likely to get. Okay. Now, moving further back down. So the table shows these daily values in the bottom row. If we treat this row as an array named A, which is in 4.3, we now want to find a non-empty contiguous subarray, the maximum subarray. So by way of illustration, for an example, we want to consider the array of figure 4.3, which is this guy right here, okay? And what we get is the following. Somebody is here. So what we get from that is the following. You'll notice that these are the different days by which there were, right, these are the different days by which there were changes in the price of the commodity, all right? That doesn't mean that simply by subtracting high from low that you'll know exactly how well it is or is not going for you, all right? So given a subarray of 0 to 16, which would be 1 to 16, or I should say 0 to 15 is 1 to 16, and A8 to 11 equals 43. Let's take a look. So here you have 38, and then there you have a -7. All right. So if we have 38, then what we have is the following. And let me find this so I can relate it to you properly. So before day 8 or day 7, if we sell it early, we can actually maximize our profits by day 11, creating a profit of $43 per share. Now, this transformation may not seem to help, but we still need to answer the check of n minus 1 over 2 and whether or not that equals n squared subarrays for a period of n days. So exercise 4, 1 to 2, asks you how to show this. Let's see. Okay, I might have skipped the word. So it asks you how to um, adhere to this particular part here, although the computing cost of one subarray might take time proportional to its length of the subarray when computing all n squared. Now here's the question. At which point do we not actually have to worry about facing computer computer oh boy, computer complexity classes given the actual items being sold? Think about it. Here you have all n squared subarray types, right? Now what we want to do is to be able to find the maximum difference between lows and highs. So now computing the cost of ownership of one subarray might take time proportional to the length of the subarray. When computing all n squared subarray sums, we can organize the computation so that each subarray sum takes one time, given the values of previous corrupted subarray sums, so that the brute force solution takes place in n squared time. Everybody get that part about n squared time and why?
Uh, Not exactly, no.
Okay, so remember before that you were saying that if we were to compare all of the different items together, then we would have a running time of one, let's see, in the event that we have, just let somebody in. So in the case that we were to try to solve this thing with the brute force method, we will most likely be having a we will most likely be having an issue with having the correct information. All right. The maximum subarray problem is for well, it's a workaround from the naive method because with the naive method, we had to go through all possible uh, subsets to try to look for an answer. And once you have that going for you, that's 2 to the n time complexity. All right. So now we're looking for some other workaround. Is that clear?
Yeah, I get that.
Okay, great. So now in our book, we have the following thing. We have something called divide and conquer algorithms. How do they work again?
You make the you try and divide like the big problem into multiple sub-problems.
Okay, what else? Okay, so we try to split up the major problem into subproblems. And then what we also try to do is merge those solutions back together. So now in the case of the subarray, they're showing us how we get to the point where um, certain things are molded or recycled or something to that effect, where we don't necessarily uh, pick through, I guess you could say, garbage, looking for something to work a bit better, right? We want to optimize our solutions. That way they'll have the minimal running time possible. Is that clear? Minimal running time possible. Who does not get that? Okay, I see no hands up. Any questions thus far? Okay. So now a subarray is going to have to go from low to high, okay? And it's going to have those elements that suggest that we are um, seeing that there's a connection between that low and high interface. 1 second, let me just um, find more material. I think I should have, did I start this session? Let's see. Well, I don't see right this moment. 1 second. Um, okay, so there is a maximum strategy in which one must lie exactly one of these places, or this is, the maximum subarray will consist of its appearance in a certain place after after the subarray is somehow not handled properly by the previous people. All right, 1 second. Okay. All right. So here we are. Okay. And we're looking at subarrays. And here's what they do as a solution. So if you could find nearly all maximum subarray crossings in the midpoint in times linear than the size of the subarray, which is A from low to high. This problem is not smaller. It's not a smaller instance of our original problem because it has, or because it has added the added because it has the added restrictions that would let's see, how come I'm not seeing, because it has the added restrictions that the subarray, it must choose cross the midpoint. Okay, so let's see what that means. Apparently somebody might be trying to sign in. Okay, so I don't think anybody's trying to tie in with the other Zoom class. Just keeping it open just in case. All right. So previously, we had the array chosen such that it restricts the subarray, and whatever is on the sorted set side chooses what entry that sorted set will become. So now let's see. Let's just take a look at what we have down here. Find max crossing subarray. This is pseudocode. By show of hands, how many of you have done pseudocode before?
Yeah, I've done it before.
Okay, great,
I've done it as well.
great. So about 2 people have done pseudocode before. So here's what it means. You see this part right here, the saying that the left sum is equal to negative infinity and the right sum is equal to positive infinity. And now you have for mid down to low, sum equals sum of AI, and sum is greater than sum of left sum. So sum maxes left. Now, there are also other files that are, I should say, there are also other offerings that that talk about the same thing over and over again. Even the there are certain places where I didn't expect to see it, which happen to float around. Okay, so finding the maximum subarray and the min subarray should not be extra difficult. Okay, does that answer anybody's question? I don't see any fingers raised. All right, 1 second. And we'll take a look at the sources in a few moments. Now, in the case of public classes, they hold hello and on tree instead. The extension allows for a manual sign up for the account. You have to speak to your governor soon. So now, let's see. I've been meaning to. So I've been meaning to talk about how this whole thing breaks down. All right, left and right. So here we have the following scenario that helps along. Let's suppose that we have 2 different loops, okay? And we need to actually move between high and lows. So here you have an equation mid plus low plus, or mid minus low plus 1 plus high minus mid equals high minus low plus 1. Everybody see that? Come on. Yes or no?
Yes.
Yeah.
All right.
Yep.
Great, 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 great. All right. So now we update the left sum to this subarray's sum. Here they're talking about the 2A subarrays. All right. They put it in line 4, 6, and then in line with 7, they will update the param of the variable match to record this index I. Okay. So then you have lines I of 8 of work that analogously call for here you have line 8 to 14, right? They work analogously and for the right half. Okay. And the for loop of lines 10 to 14 start at the index times j at mid and 1 and works up from there. Okay. So now moving further on, we have the following. Finally, line 15 returns the indices max left 0 and max right um, to yikes, lost my place. Sorry about that. Finally, line 15 returns the indices max left and max right that demarcate a maximum subarray value. All right. So let's take a look at what some of this stuff means. If the subarray A low high contains n entries so that n equals high minus low, how come I'm still losing my place? Okay. And so now here's what we have as a result. Okay. Result is as follows. So if the subarray contains n entries, claim that the call pre-find max or find max crossing subarray a low, I'm sorry, a low, mid, high. They said it takes time. Okay. So now since each interpretation, each iteration of each of the two altogether, sorry, but my eyes are just like so blurry right now. Where was I? Uh, since the iteration of each of the two for loops, there we go, takes constant time, we need to count up to many iterations there are, or how many iterations there are altogether. All right. So that is how that there works. But now let's see what the actual answer was and how we break it down systematically. So in this case, they wrote pseudocode for a divide and conquer algorithm, and it's supposed to solve the maximum subarray problem. All right. So here's what it does. Find maximum subarray. It takes an array, it takes a low and a high value. Then high, if it's the same as low, return low. And high over 2. Okay. Now in the second place, if the mid of the actual queue was less than 2, then follow the right hook, or less than 2. It says, all right, you're going to want to move from left low to left high and left sum, which would be equal to the minimum spanning tree of A from, or for A, and let me just make sure I am quoting this correctly to you. We would find the minimum spanning tree given a subarray of type 4. There we go. So now moving further down, get the following. Here we have the divide analysis algorithms, all right? And we're going to use that to break into that book over there. Now, does anybody remember how an algorithm is defined?
An algorithm is a set set of steps that have to be done in a specific order.
Okay, so that's how that goes. All right, so the algorithm is a problem-solving solution whose instructions are in sequence. All right, great. So now, okay, they're going to get to a very hefty part of the material. I'm going to, I guess, give you your break if you just got here. If you didn't, you could still take a break anyway. And I will see you in just a few minutes. All right. Okay, everybody. So I'm just trying to segment this thing into 30-minute sessions. I'm just going to stop the recording at this